Hey, welcome back to my channel. Hey, I've just learned that my flat earth videos are starting to get copyright claimed. That's cool. I see that as a compliment. I don't know why, I just do. Okay, let's continue watching the videos. On my last video, we watched this one. Now we're gonna watch this one. Emphasis. I'm not sure what they mean by emphasis. Just the word emphasis. But let's find out.
It is difficult to teach in a linear manner when the information I share branches out in multiple directions. Please bear with me. As you will see, I frequently bounce back to principles taught in prior lessons. We wouldn't be building on a foundation if we were not building upon prior lessons. With that being said, I'd like to emphasize some things here in Lesson 3, wherein I explained how the Earth curvature calculator was wrong. The purpose of the lesson was not to merely debunk the Earth curvature calculator, but
you made an emphasis. It's the name of the video. Emphasis? Made an emphasis on doing so.
Use that as an example of how people often forget to take the effects of the atmosphere into account. The aim was to help make you aware of the effects of the atmosphere, so you can remember to take them into account when people ask you questions. One such question can be found here. Many have asked, if the Earth is flat, why can't someone in California pull out a super telescope and see China? Let's watch Bill Nye the Science Guy as he makes a similar claim.
Is the Earth flat or round? It's round. Okay, now let's see. How do we go about proving that? Go to the seashore. Go to a seashore and figure out why you can't, if you live on the East Coast, figure out why you can't see Spain from the East Coast of North America.
If linear perspective were the only factor in play, a person would be able to see that far with a super telescope. But it is not possible because our range of vision is limited by more than a mere vanishing point. It is limited by the effects of the atmosphere that people are failing to take into account.
Reflection? I guess. But on a super duper clear day, which does happen every once in a while, you should be able to. Okay, let's see this guy explain more. There's a little bit left, but let's continue it.
Over the next few lessons here, I'm going to go back and expound upon some of those atmospheric questions many of you may have. Your comments are appreciated.
Okay. I'm not gonna make any, but okay. Let's continue. Reflection and Snell's law. Geometric optics. Physical. Okay. I don't know. Okay. Let's watch it.
In the last couple of videos, we talked about reflection, and that's just the idea of the light rays bouncing off of a surface. And if the surface is smooth, the incident angle is going to be the same thing as the reflected angle. We saw that before, and those angles are measured relative to a perpendicular. So that angle right there is going to be the same as that angle right there. That's essentially what we learned in the last couple of videos. What we want to cover in this video is when the light actually doesn't just bounce off of a surface, but starts going through a different medium. So in this situation, we will be dealing with refraction. Refraction, you still have the light coming in to the interface between the two surfaces. So that's the perpendicular right there. Actually, let me continue the perpendicular all the way down like that. And let's say we have the incident light ray coming in at some angle theta 1, just like that. What will happen? And so let's
Theta 1. Sounds so professional. Man. Sound professional.
say that this up here, this is a vacuum. Light travels the fastest in a vacuum. In a vacuum, there's
the fastest in a vacuum.
nothing there. No air, no water, no nothing. That's where the light travels the fastest. And let's say that this medium down
Have they defined the nothing yet?
here, I don't know, let's say it's water. Let's say that this is water. All of this. This is all water over here. This was all vacuum right up here. So what will happen? And actually, that's kind of an unrealistic, well, just for the sake of argument, let's just say that we have water going right up against a vacuum. This isn't something that you would normally just see in nature, but let's just think about it a little bit. Normally the water, since there's no pressure, it would evaporate and all of the rest. But for the sake of argument, let's just say that this is a medium where light,
just for the sake so they can get the point across,
will travel slower. What you're going to have is this ray is actually going to switch direction. It's actually going to bend. Instead of continuing to going in that same direction, it's going to bend a little bit. It's going to go down in that direction, just like that. And this angle right here, theta 2, is the refraction.
Theta 2.
That's the refraction angle.
I like the names they give these things. Theta 1 and
angle
theta
of
2.
refraction. This is the incident angle or angle of incidence, and this is the refraction angle, once again, against that perpendicular. And before I give you the actual equation of how these two things relate and how they're related to the speed of light in these two media, and just remember, once again, you're never going to have vacuum against water. The water would evaporate because there's no pressure on it and all of that type of thing. But just to, before I go into the math of actually how to figure out these angles relative to the velocity,
is it gonna say anything about what is putting pressure on the water, or what mechanism causes that? Because I would be interested to know what this guy thinks it is.
Of light in the different media. I want to give you an intuitive understanding of not why it bends, because I'm not telling you actually how light works. This is really more of an observed property. And light, as we'll learn as we do more and more videos about it, can get pretty confusing. Sometimes you want to treat it as a ray, sometimes you want to treat it as a wave, sometimes you want to treat it as a photon. But when you think about refraction, I actually like to think of it as kind of a bit of a vehicle. And to imagine that, let's imagine that I had a car. So let me draw car. So we're looking at the top of the car. So this is the passenger compartment, and it has 4 wheels on the car, and we're looking at it from above. And let's say it's traveling on a road. It's traveling on a road. On a road, the tires can get good traction. The car can move pretty efficiently, and it's about to reach an interface. It's about to reach an interface where the road ends, and it will have to travel. It will have to travel on mud.
An interface? Well, road becomes mud. I don't think that's called an interface. I think that's called a transition. Yeah, it's a transition, dude.
It will have to travel on mud. Now, on mud, obviously, a tire's traction will not be as good. The car will not be able to travel as fast. So what's going to happen? Assuming that the steering wheel isn't telling it to...
Depends how fast you're going, actually. It depends how fast you're going.
turn or anything. The car would just go straight in this direction. But what happens right when, which wheels are going to reach the mud first? Well, this wheel right here is going to reach the mud first. So what's going to happen? There's going to be some point in time where the car is right over here, where these wheels are still on the road. This wheel is in the mud, and that wheel is about to reach the mud. Now, in this situation, what would the car do? What would the car do? And assuming that, the engine is revving and the wheels are turning.
The engine is revving. And I've been mudding a little bit, so I would actually know about this. Let's see if he gives an accurate representation of what that car will do when it hits the mud.
At the exact same speed through at this, the entire point of this, the entire time of the simulation. Well, all of a sudden, as soon as this wheel hits the medium, it's going to slow down. This is going to slow down, but these guys are still on the road, so they're still going to be faster. So the right side of the car is going to move faster than the left side of the car. So what's that going to happen? I mean, this is you see this all the time. If the right side of you is moving faster than the left side of you, you're going.
It depends how deep the mud is, dude. It really does. You can keep going straight. It depends on how deep the mud is and how fast you're going.
To turn, and that's exactly what's going to happen in the car. The car is going to turn.
Not necessarily.
Turn in that direction. And so once it gets to the medium, it'll now travel. It'll now turn from the point of view from the car turning to the right, but it'll now travel in this direction. It will be turned when it gets to that interface. Now, obviously, light doesn't have wheels and it doesn't deal with mud, but it's the same general idea. When I'm traveling from a faster medium to a slower medium, you can kind of imagine the wheels on that light on this side of it, closer to the vertical, hit the medium.
The light has sides? She's saying light has sides. Wow. Oh my god. I don't think that would happen. It's possible. I don't think so. I don't even feel comfortable saying that it's possible.
Medium first, slow down so the light turns to the right. If you're going the other way,
Slow down.
if you were going the other way, if I had light coming out of the slow medium, so let's imagine it this way. Let's have light coming out of the slow medium, and if we use the car analogy, in this situation, the left side of the car is going to, so if the car is right over here, the left side of the car is going to come out.
I think this is a false analogy. I don't know, but it's a false analogy in my opinion.
First, so it's going to move faster now. So the car is going to turn to the right, just like that. So hopefully this gives you a gut sense of just how to figure out which direction the light's going to bend if you just wanted an intuitive sense. And to get to the next level, there's actually something called Snell's law. Snell's law. And all this is saying is that this angle, so let me write it down here. So let's say that this velocity right here is velocity 2, this velocity up here was velocity 1, going back to the original. Actually, let me draw another diagram just to clean it up. And also I have that vacuum water interface example. I'm not enjoying it just because it's a very unnatural interface to actually have in nature. So maybe it's vacuum and glass. That's something that actually would exist. So let's say we're doing that. So this isn't water, this is glass. So let me redraw it.
Right.
And I'll draw the angles bigger. So let me draw perpendicular.
You should probably erase that instead of drawing a new doodle. That's nitpicking, but I don't care.
And so I have our incident ray. So in the vacuum, it's traveling at v1, and in the case of a vacuum, it's actually going at the speed of light, or speed of light in a vacuum, which is c, or 300,000 kilometers per second, or 300 million meters per second. Let me write that.
or 186,000 miles per second.
So c is the speed of light in a vacuum, and that is equal to 300. It's not exactly 300. I'm not going to significant digits. It's true to 3 significant digits. 300 million meters per second. This is light in a vacuum. Light in vacuum. And I don't mean...
I can tell you specifics. I'm gonna take the time to look it up. How fast is light in a vacuum? See what it says. 299,792,458 kilometers per second. Exactly. He didn't want to go into specifics, but I will. Thank you. Okay. Let's get back to it.
The thing that you use to clean your carpet with. I mean an area of space that has nothing in it. No air, no gas, no molecules, nothing in it. That is a pure vacuum, and that's how fast light will travel. Now, it's traveling really fast.
Okay, these people haven't told us what nothing is. What is nothing?
There, and let's say that this is, and this applies to any two medium, but let's say this is, let's say it gets to glass here, and in glass it travels slower, and we know, for example, this side of the car is going to get to the slow medium first, so it's going to turn in this direction, so it's going to go like this, and we call this V2, and maybe I'll draw it, if you wanted to view these as vectors, maybe I should draw it as a smaller vector, V2, just like that, and the angle of incidence is theta 1, and the angle of refraction is theta 2. And Snell's law just tells us that the ratio between V2 and the sine, remember SOHCAHTOA, basic trig function, and the sine of the angle of refraction is going to be equal to the ratio of V1 is going to be equal to the ratio of V1 and the angle of incidence, and the sine of the angle of incidence.
Well, let's look that up now. Okay, Snell's law. Here's equation. N1 sin. Yeah, I'm not good enough. Relative incidence, refraction, and when falling to light or other waves passing through a medium, I think. Let's see if we can get anything else. No, sides of formula used to describe the relationship between the angles and refraction when falling to light or other waves passing through a boundary between two different isotropic media, such as water, glass, or air. I guess he's right. Again, I'm not smart enough to know whether he's right or not, but I'll say he's right on that.
Sine of theta 1. Now, if this looks confusing or all, we're going to apply it a bunch in the next couple of videos. But I want to show you also that there's many, many ways to view Snell's law. You may or may not be familiar with the idea of an index of refraction. So let me write that down. Index of refraction. Index, or refraction index.
Yeah, I was about to say that. Refraction index. You had it backwards.
Fine, and it's defined for any material. There's an index of refraction for a vacuum, for air, for water, for any material that people have measured it for, and they usually specify it as n, and it is defined as the speed of light in a vacuum That's c divided by the velocity of light in that medium. So in our example right here, we could rewrite this. In terms of index of refraction. Let me do that actually, just because that's sometimes a more typical way of viewing Snell's law. So I could solve for v here. One thing I can do is just, if n is equal to c divided by v, then v is going to be equal to c divided by n. And I can multiply both sides by v if you don't see how I got there. The intermediary step is you multiply both sides times v, you get v times n is equal to c, and then you divide both sides by n, you get v is equal to c over n. So I can rewrite Snell's law over here as instead of having v2 there, I could write, instead of writing v2 there, I could write the speed of light divided by the refraction index for this material.
Is it c or is it c squared? I don't know.
Right here. So I'll call that N2. Right? This is material 2. Material 2 right over there. Right? That's the same thing as V2 over the sine of theta 2 is equal to V1 is the same thing as c divided by N1 over sine of theta 1. And then we could do a little bit of simplification here. We can multiply both sides of this equation. Well, let's do a couple of things. Actually, the simplest thing to do would actually take the reciprocal of both sides. So let me just do that. So if we take the reciprocal of both sides of this, you get sine of theta 2 over.
I wish I was smart enough to know if he was right about any of this, but I'm just not. I'm a layman. I'm the layman.
Over c n2 is equal to sine of theta 1 over c over n1. And now let's multiply the numerator and denominator of this left side by n2. So if we multiply n2 over n2, we're not changing it. This is really just going to be 1. But this guy and this guy are going to cancel out. And let's do the same thing over here. Multiply the numerator and the denominator by n1. So n1 over n1. That guy, and that guy are going to cancel out. And so we get n2 sine of theta 2 over c is equal to n1 sine of theta 1 over c. And now we can just multiply both sides of this equation by c, and we get the form of Snell's law that some books will show you, which is the refraction index for the slower medium, or for the second medium, the one that we're entering, times the index of the sine of the index of refraction is equal to the refraction index for the first medium times the sine of the angle of incidence, the incident angle. So this is another version right here.
My head just won't fit all this in. It's not because I'm dumb. It's Okay, I'm only talking about myself here. When the cerebral palsy is like, for me, it limits how much knowledge I can fit in my head at one time. So like all of this and like checking it, I don't think I couldn't do that. I couldn't even learn it. It's way too much at one time. I mean, I'm a quick learner, but I mean, I don't know. I don't think I could learn this and then work it out.
This is another version right there of Snell's law. Let me copy and paste that. And if this is confusing to you, and I'm guessing that it might be, because especially if this is the first time that you see it, we're going to apply this in a bunch of videos, in the next few videos. But I really just want to make sure you're comfortable with it. So these are both equivalent forms of Snell's law. One deals with the velocities, directly deals with the velocities right over here, the ratio of the velocity to the sine of the incident or refraction angle. And here it uses the refraction in the index of refraction, where the index of refraction is really just tells you it's just the ratio of the speed of light to the actual velocity. So something where light travels really slowly, this will be a smaller number, and if this is a smaller number, this is a larger number. And we actually see it here, and you're going to see a little tidbit of the next video right over here. But here's a bunch of refraction index indices for different materials. It's obviously 1 for a vacuum, because for a vacuum, you have the refraction index is going to be c divided by the speed of light in that material. Well, in a vacuum, it's traveling at c. So it's going to be 1. So that's where that came from. And you can see in air, the speed is only slightly smaller. This number is only going to be slightly smaller than the speed of light in a vacuum. So in air, it's still pretty close to a vacuum. But then for a diamond, it's traveling a lot slower. Light is traveling a lot slower in a diamond than it is in a vacuum.
Well, I want to check that actually. Speed of light going to a diamond. Wow, that is slow. On 24 million meters a second. Wow. Well, it said it right there, but 1.24 times 10 to the miles a second. Wow. Well, that's what that is. 124 million meters a second. Billion. That, a billion. 124 million. Okay, that's a million. 124 million. God damn. That is slow. Well, let's see this little chart right here. Go in real deep, see if we can. Oh, whoa, uh-oh. What happened? Shit. Oh, no. I done fucked it up. Yep, I did fucked it up. Hold on. Shit. Fucked it up. I got it though. I think I can fix it. I can fix it. I can fix it. I fucked it. I can fix it. Okay. Okay. No. Oh, no. What about here? Continue. I was trying to look at that chart and I messed it up, and I'm not going to do that anymore, so let's keep playing the video.
Right over here. But here's a bunch of refraction index indices for different materials. It's obviously 1 for a vacuum, because for a vacuum, you have the refraction index is going to be c divided by the speed of light in that material. Well, in a vacuum, it's traveling at c. So it's going to be 1. So that's where that came from. And you can see in air, the speed is only slightly smaller. This number is only going to be slightly smaller than the speed of light in a vacuum. So in air, it's still pretty close to a vacuum. But then for a diamond, it's traveling a lot slower. Light is traveling a lot slower in a diamond than it is in a vacuum. Anyway, I'll leave you there. We're going to do that in a couple of more videos. We're going to do more examples using Snell's law. Hopefully you got the basic idea of refraction. And in the next video, I'll actually use this graphic right here to help us visualize why it looks like this straw got bent. And
Okay, that was educational. I couldn't really do anything with it, but okay. Skyline skepticism. Oh crap. The Lake Michigan Mirage. Let's see how long the video is. I don't know about. It's 4 minutes. No. Crap, I keep doing that. What the hell, let's watch it. More music.
Every
I
day
always
is
get
different.
copyright
The
claimed
views you see
with
across
music.
the lake or the lake shore, the waves, the clouds, the sun, everything's different. It's always something unique to see. It's a new experience every single day.
Joshua Nowicki captures it all through a lens. He's an amateur turned semi-pro photographer.
I moved to Southwest Michigan about 4 years ago and just fell in love with living along the lake. And photography just kind of took off from there.
Some photos he takes for work, some he sells, but most he snaps just because he loves it.
The time out here along the lake taking photos is very precious to me. It's extremely relaxing, everything else.
My precious. Okay, I'm done.
Just melts away and I can focus on taking photos and enjoying the moment.
A year ago was one of these precious moments that went viral. And I thought I wasn't going to get anything that would beat this until I found this photo from Grand Mere State Park. This is from Joshua Nowicki. And what you're seeing here is a mirage. A year ago, I showed this amazing picture on air and online. The story has been one of the most viewed stories on our website ever. Most click because of its rarity, and also because there are skyline skeptics. They say my explanation is a cover-up. A cover-up to their belief that this picture is proof the Earth is flat. Here on the shores of Lake Michigan at Warren Dunes State Park, just 50 miles towards our west is Chicago. However, we can't see the skyline, at least from this vantage point.
Earlier this year, there was a really good chance. It looked like probably 40 or 50 buildings looked visible from the top of the dune over here, which is the most I have ever had a chance to see it.
Is it evidence of early philosophers that the world isn't round? Or is it a mirage?
If you follow this right here, it's really easy, right through here.
We climb the dunes to find out.
A mirage is a case of atmospheric refraction, and it's caused by the fact that you have temperature variations in the atmosphere, and these cause density variations.
Dr. Mark Rennie is an associate professor of aerooptics at the University of Notre Dame.
So literally the speed of light varies within the air, and this variation of the speed of light has the effect of bending light rays.
Sometimes the Lake Michigan waters makes us see things. Here we are at the top of Warren Dunes. Pretty exciting as the inversion is setting up as we speak. A spring night, the lake waters are still very cold. And we can see out on the horizon and above it a dark line that's starting to show up just above. That's the inversion. That's where temperatures are different below than they are above and creating that cap. And we're beginning to see that atmospheric lensing, where in spots along the horizon we're seeing either breaks in the buildings or where the buildings may be flipped or a distortion caused by the mirage or atmospheric conditions that are changing as we speak.
What's happening is the light from Chicago is being bent by the cold air above Lake Michigan slightly downwards towards the observer here in Michigan. And that's helping the light rays get around the curvature of the Earth, so to speak, so that Chicago can be seen almost all the way down to ground level.
See, now there's buildings shown up straight ahead of us. But if it is a mirage, argues many of the biggest critics who've emailed me, the image should be upside down.
The word mirage originates from the same root word as the word mirror. So technically, I think if you're going to be a stickler about it, you would say a mirage has to have an inverted image. But again, the physics is all the same.
The science is the same of that of a lens. Here's a simple example.
So if you're looking at Chicago here, now you can just see the top of the Sears Tower, and if our simulated temperature inversion moves into place, hopefully now you can see pretty much all of Chicago,
see all the lower buildings,
including what's the ground level.
So the atmosphere really is acting like a lens.
Yes. So this is, if anything, this is definitely a demonstration that that refraction displaces the image, and basically where you think the image is not where it actually is.
That picture from a year ago, that's looming, as are these photos that we snapped. This is a mirage. We caught this looking towards Michigan City. Notice the distortion or flip in the image in the time lapse. On a normal day, say in the summer, you can see Chicago, but only a dozen or so of the tallest buildings.
Anything more than that, especially once you get over 10 or 12, something's happening, because that's not usually there.
The views along the lake are always changing, along with the weather.
It's always different. It's so unpredictable that I want to catch as many different views of it that I can.
That explains things, dude. That explains things perfectly. I don't know what they're gonna try to debunk it now. The next video, yep, the next video, I think they're gonna try to debunk it. Alright, let's see. Oh. Extension. I think that's it. I think I'm gonna end it here. I mean, yeah, I'm gonna end it here. Thank you for watching, and keep playing with yourselves.